Lesson 4-7, weighted averages, and in this lesson you learn to solve mixture problems and to solve problems involving uniform motion. Why is it important? Because you can use weighted averages to solve problems involving travel, transportation, and chemistry. Let's take a look at this real-world example. In Mr. Calloway's American History class, semester grades are based on 5-unit exams, and these are your 5-unit exams. One semester exam and a long-term project. Each unit exam is worth 15% of the grade, and the semester exam is worth 20% of the grade. The project is worth 5% of the grade. Parker's scores for the semester are given in the table at the right. If 100% is a perfect score for each item, find Parker's average for the semester. Okay, so in this case, in order to find Parker's average for the semester, you may want to add the percentages and then divide the number by the items, which is 7. But this is suggesting, or this assumes, that each has the same weight. So in this case, you need to find the weighted average of the scores. Before we do that, let's define weighted average. Definition of weighted average: the weighted average M of a set of data is the sum of the product of each number in the set and its weight divided by the sum of all its weights. Okay, so you can find the weighted average for the application above by multiplying each score by the percentage of the trimester grade that it represents and then dividing the sum of the weights, or 100, which is 100%. Okay, so you have 5 times 15, 1 times 20, and 1 times 5 should equal 100. So if you write it out, you now have 15 times 79 plus 83 plus 96 plus 91 plus 89, because these are all Parker's grades for the 5-unit exams weighted at 15%. Okay, and then you have 20 times 90, because 90 is the semester exam and 20% is the weight, and the project is 95, the grade is 95, and the weight of the project is 5 divided by the total weights, which is 100. Okay, so doing that, we add up all the numbers in the parentheses, multiplied by 15, added to 220 times 90, added to 5 times 95 will get us 8,845, and then divide that by 100. So Parker's average is 88.45. Okay, so his average for the semester is around 88%. Okay, let's go to the fun part. So that's an easy way to find weighted average of your grades. Okay, mixture problems involve weighted average as well. In mixture problems, the weight is usually a price or a percentage of something. Suppose the Central Perk coffee shop, not office, sells a cup of espresso for $2 and a cup of cappuccino for $2.50. On Friday, Rachel sold 30 more cups of cappuccino than espresso, and she sold $178.5 or $178.50 worth of espresso and cappuccino. How many cups of each were sold? Okay, so if you know this series, this is the series Friends. Okay, and it's really called Central Perk Coffee Shop. Anyway, let's move on. So what do we know? We need to find out how many cups of each were sold. So we need to come up with a let statement. So in this case, our let statement would be let E represent the number of cups of espresso sold. Then E plus 30 represents the number of cups of cappuccino sold. Why E plus 30? Because it says there that Rachel sold 30 more cups of cappuccino than espresso, and that's the reason why we represented cappuccino as E plus 30. Okay, so after we have done our let statement, we need to create an organizational chart such as the one that you see here. Okay, and in our organizational chart, okay, we need to create a formula which simply means that the number of cups okay, multiplied by the price per cup should equal the total price. So this is a formula, and we'll explain that in the next slide, okay, that you will use in a mixture problem. In a mixture problem, you will always have a formula on the top part, and you will have what you are mixing on the left part, or on the vertical part of our organizational chart. Okay, so you have espresso and cappuccino. That's what we're trying to mix. And we know that according to our let statements, the number of cups of espresso, we represented it as E. Okay, and the price per cup of the espresso is $2. So therefore, if we follow this formula, the total price should be 2E. For cappuccino, it's E plus 30. And then the price per cup of cappuccino is $2.50. If you follow this formula, it's going to be 2.5 times or plus E plus 30. Okay, and solving this problem, okay, we basically add these two. Okay, add the total price of espresso plus the total price of cappuccino. Okay, and when we add them, it should equal the amount she sold, which is $178.50. Okay, and if we write this out, so the total price of espresso, like what we mentioned, plus the total price of cappuccino will be equal to the total sales. Total price sales of espresso is 2E. Total sales of cappuccino is 2.5 times the quantity E plus 30, which will be equal to $178.50. And solving this equation, okay, we distribute 2.5 to E and 30, which now becomes 2.5E plus 75. And then we add like terms, we end up with 4.5E plus 75. Subtract 75 to both sides, we end up with 4.5E equals 103.5. And we divide both sides by 4.5, end up with E equals 23. So there were 23 cups of espresso sold. And let's go back to our let statement. Our let statement said that cappuccino is represented by E plus 30, and we know that E is 23. So 23 plus 30 equals 53, or 53 cups of cappuccino were sold. Okay, and finally, let's do the examined part of this. If 23 cups of espresso were sold, the total sales of those cups of coffee would be 23 times $2, or $46. If 53 cups of cappuccino were sold, the total sales of those cups of coffee, using a calculator of course, would be $132.50. And finally, if we add those two amounts together, we end up with $178.50. Okay, and the solution is correct. And this is a good example of a mixture problem, and this is something that you need to know right here. So in a mixture problem, there is always a formula you use. Okay, so it may be a coin problem for mixture, wherein the formula that you will use will be coins times the value of the money, value of the coins, which will equal the money. The money problems that involve cost, this is where Rachel's example come in. The amount times the unit price equals the money spent. Dry mixture problems, which is amount of times the unit price equals the money spent. Solution problems involving percent, which is the volume times the percent of concentration equals the amount in solution. And investment problems, which is principal times percent rate equals interest. And you might ask yourself, why is it that there is no time? Remember, we discussed in the last chapter that interest equals principal times rate times time. So in this case, it's only principal times rate. Why is there no time? Because it is assumed in investment problems, the time is always 1 year. So your time here is 1 year. So if it's 1 year, then it's the same as just multiplying principal times percent rate, because of the identity property of multiplication. Hope that makes sense. Another thing that's very useful is what you just saw, is creating an organizational chart. Okay, so when we create an organizational chart, okay, we create something like this. Let me insert a table here. Okay, okay, so this is the table that you want to use every time. Let me extend this. Okay, and on that table, this is where your formula will come in, right here. Any of the formulas that you have right here, okay, you will be putting on top. And this is the, on the side will be the items you mix. And the bottom part will always be the total. Now it is also very important to know that you don't have to fill all the cells, okay, in this in this problem, but you need to create this organizational chart every single time, and that's exactly what happened to Rachel's example, okay, where the cell was created. And if you look back to Rachel's example right here, now everything will be gone, and I will be, nope, not that one. Okay, let's go down here. Okay, so if you look at the bottom part of it, let me fill it up again. There you go. It's actually very similar to our organizational chart, but if you notice, okay, if I do this and this, oh, not straight, do that again, do this straight line, and down here and create another straight line here, all the way down here. Okay, this is very similar to our, okay, organizational chart. The total is here. Oops, sorry, the total is there. Okay, and I would be putting 178.5 here, and I will just be adding 2e plus 2.5e equals 178.5. Okay, let me show it to you in. So let's take a look at example number 2, and let's see how using the formulas will affect this problem. An advertisement for an orange drink claims that the drink contains 10% orange juice. Jamel needs 6 quarts of the drink to serve at a party, and he wants the drink contain only 40% orange juice. How much of the 10% drink and pure orange juice should Jamel mix to obtain 6 quarts of a mixture that contains 40% orange juice? Okay, so this is the scenario. Jamel needs 6 quarts to serve at the party, and he wants that 6 quarts to contain 40% orange juice. So he has 10% orange juice and pure orange juice. He wants to find out how much to mix with the 10% orange juice in a pure orange juice, so that he can obtain 6 quarts of a mixture that contains 40% orange juice. Now, using that formula, I'll use a different table. Well, not really a different table, but the table that we just talked about, an organizational chart that we just talked about. And let's see how we do that. Let me insert myself a table, okay? And let me get that table right now, okay? So this is the table. We'll make it smaller, obviously. There you go. Okay, using that table, I'll put it here because I'm going to show you how this will be very similar to the one that's been used in the book. So this is the table we talked about, and the formula on top would be this one right here. Okay, solution problems involving percent means the volume, okay, times percent concentration will be the amount in the solution. Okay, so this will be our volume. Okay, okay, percent of concentration will be the, okay, amount in solution. So this will be amount in solution. Remember, we talked about on this side will be what we are mixing, and the bottom part will be the total. So in this case, we'll be mixing, let's say, Sunny D and Tropicana. We'll just name our orange juices, and this will be total. Okay, so Jamel wants to mix Sunny D and Tropicana so that at the end he'll end up with 40% concentration of the two. So at the end he'll have 40% here, and at the end also here he'll have 6 quarts total volume. Okay, so let's start. We always start with a let statement. So in this case, we let P represent the amount of pure juice to be added. So let's say Tropicana is pure orange juice. Okay, this is just an example. So if it is pure orange juice, which means that means it has 100% okay juice in it, and Sunny D is our 10%, so we only put 10%. Okay, and since the total is 6 quarts, and if we let P represent the pure juice to be added, which is Tropicana, it's logical to follow that Sunny D would be 6 minus P. Okay, so if we use that formula and we get the amount in solution, we end up with 0.1, because that is the decimal of 10% times 6 minus P. And then you get 100%, which is 1, times P, or simply P. Okay? And then what happens next is that you'll get the total, which is 6 times 0.4 right here. So what do you notice? Okay? Again, in an organizational chart, this is where we get our equation. Okay? So the last column is where we get our equation, meaning that when we add the first row to the second row, it should equal the last row. Okay? And let's see how the book uses it. It's very similar. Okay? So you have your 10% orange juice here, which is right there, and your pure juice, which is 100%, okay, and your total, which total that you want to produce, which is 40%. On the top part, the number of quarts, okay, and we let P represent pure orange juice, so this becomes 6P, same thing, okay, and the total one is 6 right here, same column, okay, percent concentration, okay. Now this one is the one that we have here at the end, which is 0.1 times 6 minus P. And then we have 100% times P is simply 1 times P equals 0.4 times 6. Okay, very much the same thing. But the only difference is that you might be confused, but because there is no additional column here. Okay, so in this case, I just took out the items being mixed, put them outside, and everything inside, okay, involves the formula. Okay, so knowing that, we now create or come up with a solution, which is the amount of orange juice in 10%, which is this one, plus the amount of juice in pure orange juice, which is that one, will equal the amount of juice in 40% juice, which is that one. So we simply substitute the values. 0.1 times 6 minus P plus 1 times P equals 0.4 times 6. Okay, simplifying it further, we have 0.6 minus 0.1p using the distributive property, plus 1 or plus p equals 2.4 will give us 0.9p. Okay, that means you subtracted 0.1 from 1p, and then you subtracted 0.6 to both sides of the equation, and then you divide both sides by 0.9, end up with 2. Okay, so there were Jamel needs to combine 2 quarts of pure orange juice with 6 minus 2. Why 6 minus 2? because our other let statement, the 10% juice, would be 6 minus P. And we substituted P with 2. Okay? So 2 quarts of pure orange juice, 6 minus 2, or 4 quarts of 10% juice to obtain a 6-quart mixture of 40% orange juice. And then I leave the check up to you. Okay? A little bit complicated, but rewind, pause, whatever you need to do, okay, to be able to understand this lesson. But the key is here. You need to create an organizational chart for mixture problems. The very top of the organizational chart will always be a formula. On the vertical part of your chart will involve the items being mixed, and there should always be a total sign at the bottom. Okay? Let's see how this works some more. Let me give you one more thing. Okay? This one is not in the book. Let me cover this. Cover. Oopsie. And then I'll cover this. And let's explain this. So Barrett's bookstore sells pencils for 10 cents each and erasers for 15 cents each. Last Tuesday, the store sold 17 more pencils than erasers for a total of $23.45. How many of each item were sold? Okay, so in this case, we use the formula, okay, the one that I gave you, amount times the unit price equals the money spent. The formula again is on the very top, and on the side are the items being mixed, in this case the pencils and the erasers, and what we talked about, the total should always be at the bottom. So let's put things where they should be. Okay, so we know that the Barrett bookstore sells pencils for 10 cents each and erasers for 15 cents each. Last Tuesday, the store sold 17 more pencils than erasers. So that means in this case, we let E be our pencils. That's our let statement. And then to be able to create a let statement for our pencils, we need to do E plus 17 because Barrett sold 17 more pencils than erasers. And then we look at the unit price for pencils, which is 10 cents, and the unit price for pencil erasers, which is 15 cents. And then follow the formula, 0.1 times E plus 17, okay? And then you have 0.15 E, okay? And then it should total 23.45. So what you want to do, you want to add that cell to this cell should equal 23.45. Okay, and let's do that problem right now. Okay, you have now 0.1 times E plus 17 plus 0.15 E equals 23.45. Let's simplify this. This is 0.1 E plus 1.7 plus 0.15 E equals 23.45. Okay, let me extend my page. And then now 0.1 E plus 0.15 E will give us 0.25 E plus 1.7 will give us 23.45. Subtract 1.7 to both sides, 0.25 E. Okay, equals 23.45 minus 1.7. Bring that decimal point down. That's a 5. That's a 7. This is a 14, and this becomes a 2. So that's a 1. 21.75. And then we divide both sides by 0.25. E will be equal to, let me make it easy for you and for myself as well. Okay, E will be equal to 87. And if we substitute 87 to our E plus 17, you'll end up with 104. So you have 87 erasers and 104 pencils. And that's how you use your organizational chart to solve mixture problems. And unfortunately, that's not the end of our lesson, because the next lesson we'll talk about uniform motion problems. You probably want to pause this, get something to drink, okay, because we're moving on. Motion problems are another application of weighted averages. When an object moves at constant speed or rate, it is said to be in uniform motion. The formula distance equals rate times time is used to solve uniform motion problems or rate problems. In the formula, d represents distance, r represents rate, and t represents time. You can also use equations and charts when solving motion problems. I'll show you how to use an organizational chart to solve a uniform motion problem. And I'm also going to show you an easier way to do this. So on Friday, Shanae and her brother Raphael, okay, went to visit their grandparents for a weekend. Luckily, traffic was light and they were able to make the 50-mile trip in exactly an hour. On Sunday, they weren't so lucky. The trip going home took exactly 2 hours. What was their average speed for the round trip? So in this type of problem, we're back to our weighted averages, okay? And then let's use weighted averages to solve this problem. And in the next problem, example 4, we'll use the organizational chart. So to find the average speed for each leg of a trip, rewrite d equals rt as r equals d over t. Meaning if we solve for r, we divide both sides by t, end up with r equals d over t. So we use the formula r equals d over t, r equals d over t for going and coming back. And then going, we have 50 miles per hour, or 50 miles per hour is what the rate is. Returning is 50 over 2, or 25 miles per hour. And then you think to yourself, okay, so that means I just have to add 50 plus 25 divided by 2, or 37.5 miles per hour, right? However, Shanae did not drive at these speeds for equal amounts of time. So this is actually not right. Okay? So that's not right. You can find the weighted average for their trip. Okay? And this is how we do it. So to get the weighted average m, you get 50 times 1 plus 25 times 2. Why times 1? Because it took them 1 hour for going and 2 hours coming back, and the total time will be 3 hours. So you multiply them by the number of hours they traveled for the trip, end up with 100 over 3, or 33 and 1/3. And this is the correct answer. The average speed was 33 and 1/3 miles per hour. Okay? Let's take a look at the other one. And this is where we use our organizational chart, and I'm also going to show you how to use this without the organizational chart. So listen up. 2 city buses leave their station at the same time, one heading east and the other heading west. The eastbound bus travels at 35 miles per hour, and the westbound bus travels at 45 miles per hour. Okay? In how many hours will they be 60 miles apart? Okay? Now, in problems such as these, you need to be able to visualize what's happening. So a good starting point would be draw a diagram to help analyze the problem. So we start off with probably the bus station right here. So you have your bus station and you have 2 buses, one going east and one going west. Okay, one going west, I'm sorry, is traveling at 45 miles per hour. The other going east is 35 miles per hour. Okay? And then it's saying that it's asking, okay, in how many hours will they be 60 miles apart? And that is the question we want to ask. Okay? So how many hours will they be 60 miles apart? And let's use an organizational chart to solve this. Organize the information in the chart. Let t represent the number of hours until they are 60 miles apart. Remember that rt equals distance. So let's use this chart. The bus there, okay, one is going eastbound, the other is going westbound, and we put the formula rt equals d. Okay, this again is our formula because we need to do that. Our rate for eastbound bus is 35 miles per hour. Our rate for the westbound bus is 45 miles per hour. This is time, okay? Same time for both of them, okay? Because at what time will they be 60 miles apart? So if we use the formula, this is 35t and this is 45t, okay? So the eastbound bus travels at 35t miles and the westbound bus travels at 45t miles, okay? And the equation that we want to use is that the eastbound distance plus the westbound distance will be equal to the total distance right here. So the eastbound distance plus the westbound distance will be equal to 60 miles. And the eastbound distance is what we right here on the chart would be not coming up, not coming up, not coming up, would be 35t right here. Let me just write it because it's not coming up. I don't know why. And the westbound distance is not coming up as well. 45t. I'm assuming this is not going to come up though, and this is not going to come out. And the total distance is 60 miles. And that'll be our equation. And solving our equation, okay, 35t plus 45t, like terms, ATT equals 3/4. Okay, but time isn't, there's no such thing as 3/4 in time, so you simply multiply that by 60. 3/4 times 60 will give us 45 minutes. The buses will be 60 miles apart in 45 minutes. And to check the answer, find the distance each bus could travel in 3/4, and if it totals 60, you're good to go. And we know that 35 times h, okay, or 3/4 h times 35, 3/4 h times 45, is it equal to 60? And most definitely it is, and our answer checks out. Okay, now through all that, there's an easier way of solving uniform motion problems, okay, and this is what I'm going to show you right now. Okay, now in uniform motion problems, okay, we always use rate times time equals distance. And let's see, there are 4 scenarios in uniform motion problems. The first one, together, then move apart. Okay, that is our example on the buses. It's saying add the rates. I'm going to tell you how to do that later in a few minutes or a few seconds. Another scenario is apart, 2 cars, 2 planes, 2 bicycles apart, and they start moving together. Again, we still add the rates. Okay. In the third scenario, we have a chase scenario. In this case, we need to subtract the rates. And the fourth scenario, wind or current, we will cover this later. Because these problems will involve a system of equations. Okay. So let's take a look at how we can apply this scenario. Suppose John and Gina leave at the same time, traveling in the same direction. Gina drives at the rate of 85 kilometers per hour and John at 70 kilometers per hour. How long until they are 90 kilometers apart? So this is a good example of a chase problem. It doesn't really sound like a chase problem, but it is a chase problem when they're moving in the same direction. If you notice, okay, there's nothing here that says moving in the same direction. So if in that case, you can consider this to be a chase problem. So if they're moving in the same direction, what is it saying? Subtract the rates. What does that mean? So that means we still get rate times time equals distance. Okay, and saying subtract the rate, so we get the bigger rate, subtract the smaller rate. So our rate is 85 minus 70, okay, multiplied by time, will be equal to the distance, in this case 90 kilometers apart. Okay, so if you do this, we end up with 15t equals 90, or t equals 6. Okay, we divide both sides by 15, so they will be 6 hours, okay, when they are 90, it will take 6 hours for them to be 90 kilometers apart. Now, if you examine how to solve this, okay, just think of this and visualize. One is traveling at 85 miles per hour and the other is traveling at 70 miles per hour. Okay, let's check how if our answer checks out. So that means every single time Gina drives faster at 15 miles per hour. So for the first hour, he is 15 kilometers ahead, right? For the second hour, Gina is traveling, he is 30 kilometers ahead. Okay, for the third hour, he'll be 45 kilometers ahead. For the fourth hour, he'll be 60 kilometers ahead. For the fifth hour, he'll be 75 kilometers ahead. And for the sixth hour, he'll be 90 kilometers ahead. And this is the way to check it as well. Okay? And that's how you use these formulas to be able to solve a uniform motion problem. Now, let's use this formula for our previous example, which is the bus. Okay? And let me light them all up again. That's the bus, westbound bus. Okay, and it's saying if they're traveling in opposite directions, okay, coming from from one point, we need to add the rates. So a shortcut method of doing this would simply be this. Again, rate times time equals distance, and we need to add the rates now. So we have 45 plus 35, and you multiply that by t, equals the distance, which is 60 miles. 45 plus 35 would be 80. T equals 60. Okay, very similar to this problem right here, which will give us 3/4. Okay, so if you notice, you have a shorter way of doing it, and you have an organizational chart to also do it in. Okay, and that's it. Sorry, this is a long lesson, and I hope you've paused it and you had to rewind if you needed to, okay, to be able to understand this. An important thing to know in algebra. Thank you for watching,